Hey guys, so I understand we're having some problems with these calculations, so I thought I'd make a quick video to run through each one to hopefully give you a little bit of help. So, first one, your weight on your planet. Well, weight is just a fancy term. Now hold on, I'm going to disappear off screen, but I'm still here. Don't worry. See, you can still hear me. Weight is just a fancy term for the force of gravity that we feel. So if you know force of gravity, you know your weight. Force of gravity is equal to big G times your mass, mass of you, times the mass of your planet, divided by the radius of your planet squared. Now, this R in here is how far apart these two objects are. And if you're on your planet, you're basically just the radius of the planet away from the center. You know, even if you stood on top of the biggest mountain on Earth, you would still be about this far away from the center of Earth. So, here's your weight. Now, you know your mass, you know G, you know the mass of your planet, you know the radius of your planet. Number one is done. That's it. Now you might be thinking, Mr. Quinn, when we've talked about this for Earth, we usually use this other formula, F little g. Instead of F little g is equal to mass times acceleration of gravity. That's also true. But for this to work, we had to have already been able to do all this stuff. So what we've been doing all year is simplifying this formula and explaining its effects here. So when you take into account how gravity works, what happens is you accelerate towards Earth. This acceleration of gravity, though, is in this formula. For instance, you are in this formula, and you are in this formula. Your weight is the same either way. We're just talking about your weight. So where does AG come from? Simple. It comes from big G, the radius of your planet, and the mass of your planet. It's everything that's left. So when you need to find AG, you would say the acceleration of gravity on my planet is equal to big G times the mass of my planet divided by the radius of my planet squared. If you were to put the mass of Earth and the radius of Earth into this formula, you would come up with 9.8. We just memorized that number so we didn't have to do this work over and over again. You're now 2 steps of the way done your calculations. Let's look at some of the other ones. You need to tell me the distance that your planet covers in an orbit and the velocity that your planet travels when it orbits. Let's slide down a little bit. There we go. Now we have a little more room to work with. All right. So, your planet orbits the sun. Here's the sun. Here's your planet. And it travels like this. Now, how far does it go? Well, if you imagine running around on a track, our track is about 400 meters long. If this is a perfectly circular track and I want to know how far you ran, an easy way to figure it out is to say, well, how far is it from the center? What's the radius of the circle? Let's call this R to the sun. Note that this radius is different than the radius of your planet. So if I know how far I am from the sun, I can figure out how far I went by calculating the circumference. Circumference, which is 2 times pi times the distance to the sun. Now, you might be thinking, Mr. Quinn, we asked for distance that you travel, not the circumference of the circle. Well, they're the same thing. Because if I were to take this line, cut it, and stretch it out, I'd have one big straight line. So I can pretend that this is a distance, and I can call it delta x for one orbit around the sun. Delta x to get around the sun is that big. Okay. But that doesn't finish my problem. The next part of that is how fast am I moving? Well, speed's a funny thing. We can't really measure it that well. So instead of measuring speed, we measure instead Sorry, the computer fell asleep. We measure instead two things: how far I went and how long it took me to go that far. So if you want to find the velocity of your orbit, you need to know two things. How far was your orbit, which we just figured out, and how long your orbit takes. It takes the Earth 365.25 days to orbit the Sun. Now, I don't know how long your planet takes to orbit, but you can find that out. That was part of your research, is to find out how long this is. If you know the time to orbit, and you know how far an orbit is, then you can tell me how fast it orbits. I've done two more calculations. Now, what else is there to do? The last part, one more part. The minimum and maximum distances, or times it would take to travel to your planet. So, let's go back to this picture. But I'm going to draw it again so we have a little bit more room to work with. Let's slide down. So here is the Sun. Here's your planet. And here's Earth. Now, if your planet is closer than Earth, you can just reverse these. But the same idea remains. If I wanted to go from Earth to your planet, the shortest distance I would ever take is this. Now, to find out how big that is, we need to know two things. How far is your planet from the Sun, R to Sun for your planet, and how far is the Earth from the Sun, R to Earth, or to Sun from the Earth. If I subtract those, I get this amount, the shortest distance I would ever travel. But sometimes Earth is all the way on the other side of the Sun, over here. In which case, I would take these two numbers and add them together. That's my total distance. Either way, what I end up with is some distance that I need to travel. Now we're trying to figure out how long it will take. So I need to know a few other things. One thing I'd like to know is the velocity I start with. Well, we're going to assume that you start out from 0, that you're just sitting on the planet not moving. So we can call this 0, and it goes away. But then it doesn't make sense. The distance is 0. We're going to have to speed up along the way. So we're going to assume we accelerate at a certain rate. We're going to pick a number, and we decided to pick the number 9.8 meters per second squared. That way, any passengers on the ship would feel like they're just standing on Earth. We would have 1 g of force pushing the whole time. So plus 1/2 a t squared. Down here, we figured out how far I have to go. I'm assuming acceleration is 9.8, so I can solve for t and find out how long it will take. Now, spoiler alert, this assumption of 9.8 for A is really bad. It's not a great idea. It would be very, very hard to keep our foot on the gas, accelerating at that rate all the way to your planet. But hopefully you'll be able to explain that when you come up with some answers. Now, the last part, your favorite part, geosynchronous orbit. For that, we need a little bit more room. So I want you to come and follow me over here. We'll work in this corner. So, that was Brendan Osborne, by the way. He wants to talk to me. Brendan, if you're watching this, I'm talking to you, but through a computer. So, geosynchronous orbit. First of all, what does that mean? It simply means that we're in orbit, and in a special kind of orbit. So you are taking the same amount of time to make it around your planet as it takes for your planet to rotate. So, here's Earth. And Earth takes exactly, well not exactly, but close to, 24 hours to spin around. So the time to rotate is 24 hours. Well, a geosynchronous satellite would sit up above the Earth some distance, and it would go around. And the time for orbit would also be 24 hours. So if I was sitting on the planet right here, and I looked up and saw that satellite, it would always be directly above my head. Geosynchronous satellites are how GPS works. It's how your cell phones work. It's also how DirecTV works. You're always pointing at the same satellite in the same place in the sky. Now, this satellite's traveling in a big circle, but the radius of this circle is kind of goofy. It's not the radius of the planet, and it's not a particular height. It's some unknown r. So let's call r, and I'll say for geosynchronous orbit. So RGO we'll call it. Now, I need to find that, but I can't figure it out here. So let's take a step back and talk about just orbit. Orbit is spelled FC equals F big G. Gravity makes me go in a circle. Now, I can rewrite these a little bit. Gravity is big G, two masses, in this case, the satellite and my planet, divided by this R, RGO. I don't know how far it is, but some distance, squared. FC, well, the thing traveling in a circle is the satellite. It's traveling at some unknown speed v, let's call this VGO, divided by RGO. Now, at this point, we can simplify this formula a little bit. One thing you might notice is the mass of satellites on both sides. We can cross those out. RGO is on both sides. We can cross this one out, but it's squared over here, so we can only cross out one. Now we end up with the velocity for geosynchronous orbit squared equals big G times mass of the planet divided by RGO. We have a problem. I don't know how fast the satellite's moving, and I don't know how high it is. But I do know G, and I do know the mass of the planet. So, what to do? Let's go back over here for a minute. The time to orbit has to be 24 hours for Earth, or whatever number it is for your planet. So I actually know how long it should take to orbit. Well, where does that time come from? It comes from how fast I'm moving around this circle. That's VGO. I'm moving at some speed, VGO. Well, if I have a velocity and a time, the only thing missing is a distance. This distance, how far I'm going in this circle. So I can use a really simple formula from back at the beginning of the school year. V equals delta x over t. And if I'm in geosynchronous orbit, I'm traveling at this speed. The time it takes me to get around is the time for one orbit, or really the time it takes my planet to rotate. So why don't we just put that in? And then I have to go some distance. Well, that distance, which we kind of did earlier with a different problem, is the circumference of this circle, the perimeter of the circle. In this case, 2 pi times RGO. VGO equals 2 pi RGO over T rotate. Now, we have another problem. I know how long it takes my planet to rotate. I know pi, but I don't know VGO and I don't know RGO. Seems like I have two problems I can't solve, except that these two things are telling me something about VGO. I'm going to write this a little bit differently. If VGO squared is this, then VGO is the square root of this. G, mass of the planet, divided by RGO. And if VGO is this and this, then I can make a big equal sign over. They're the same thing. So I can take VGO out and say square root of G, mass of my planet, divided by RGO equals 2 pi times RGO divided by the time to rotate. Now, can I solve this problem? Let's see. I know G, I know MP, I don't know RGO. I know pi, I don't know RGO, I know the time to rotate. At first glance, it looks like there's two things I don't know, but they're really the same thing. So you can solve for RGO, and you're done the problem. Good luck.